What is activity? Well, it's the number of nuclear decays per second. So please bear in mind this definition in your exams. Make sure you can recall it, okay? So what happens to activity as time passes? Well, it decreases, okay? So if you've got some unstable radioactive nucleus at the start of time, eventually it's going to emit radioactive particles as time progresses, and its overall activity is going to decrease. The units of activity are becquerels, so you need to know it can be abbreviated to capital B and lowercase q. That's its units. Now we're going to be looking at what half-life is, okay? So two definitions, okay, you can state. One is the activity of a radioactive isotope to half, okay, so it's the time it takes for the activity of that radioactive isotope to half, or it is the time it takes for the number of unstable nuclei to halve. Okay, so please remember those definitions. Okay, the way I tell students to understand this, let's say you've got a classroom of 30 students, they're all radioactive particles, and let's say every second one of them leaves the room randomly. Okay, I pick random students. Eventually, after 15 seconds, half of them will leave the room. Okay, so the half-life for that particular classroom would be 15 seconds, because in 15 seconds, half of those radioactive particles, which are the students, would have been emitted. Okay, would have left the classroom. So a short half-life means a radioactive material decays very quickly. A long half-life means a radioactive material decays very slowly, and different elements have different half-lives. Remember, radioactive decay is completely random, okay, so we cannot predict which decay will take place. So, if we look at this table here, okay, we've got the number of half-lives that have passed, and if we look at the number of radioactive nuclei, 128 to start off with isotope 1, half of that, that's 64, half of 64 is 32, okay, and we can see the trend as it continues to halve. Okay, so it doesn't matter what type of isotope, what type of radioactive element you've got to start off with, the half-life is the time it takes for half of those radioactive particles to be emitted. Okay. Right, so the other thing you need to be able to do is to work out the half-life from a graph. Very common exam question. So if we look at the y-axis, this is the count rate in counts per minute. So if we start off with 80, half of 80 is going to be 40. So if we go down here, and with our ruler we go across, and then with our ruler again we go downwards, we've got 60, and this is 60 days. So the half-life is going to be 60 days. You could have taken, let's say, we start off with 60 counts, okay? So we go across there, okay, we arrive here. In fact, sorry, half of 60 is 30, which is this point here. So we go across there, okay, and then this point here minus this point here should also give us 60 days. Okay, so here is our calculations here. So that was 84 minus 24, okay? There's several ways of doing it, but as long as whatever original amount you choose, you've got to half that, then you go across, and then you work out the difference, okay? You find the time it takes to half here, okay? So some dangers of ionizing radiation to the human body, well, cell damage, tissue damage, organ damage, okay, essentially cancer. That's simply due to, obviously, as I've told you before, the ionizing radiation getting some electrons, causing the atoms to malfunction, and which causes the cells to malfunction. So what precaution can we take in order to prevent these radioactive particles getting onto us? Well, to prevent them from being inhaled, a mask, okay, what materials should be used to line the boxes used to store radioactive materials? Well, lead, okay, that's to ensure any gamma rays are prevented from being emitted from that box. Why should people try to keep a large distance between themselves and radioactive particles? Well, you know, we've already talked about the risks. Cancer can be caused What can be used to handle radioactive sources and keep a distance away from them? Tongs or forceps. So medical traces, which we'll look in more detail in a second, have a short half-life, which means they need to be produced relatively close to the hospital, if not in the hospital. Okay, otherwise they'll run out before they actually reach the patient. But the other important reason is why that's important is we don't want them to stay in the body any longer than they need to be. Okay, because as we know, there's certain risks with ionizing radiation. But we'll look into that in more detail in a second. Okay, so if radiation reaches an object, we say that it has been irradiated. Why is this dangerous? Well, if the person literally stands next to a radioactive source for a long period of time, obviously the gamma waves obviously can infect the cells, which can cause mutations, and we can get cancer being caused. Okay, so the person himself or herself is actually not dangerous, but the actual process of irradiation is. Okay. If unwanted radioactive atoms get into a material, we say that the material is contaminated. Okay, and why is that dangerous? Well, obviously, the alpha particles or the alpha source or the beta source is actually inside the person's body, infecting the surrounding atoms and cells more closely, ionizing them, and obviously causing the cells to malfunction faster, and also we've got this ionizing radiation being given off inside the person's body. Okay, so actually that's way more dangerous than if the person's being irradiated, and this actually occurs much more quickly than a person, well, a person can develop cancer much more quickly compared to if they've been irradiated. So let's look at some uses for radiation. Well, alpha particles are used in pretty much all smoke alarms or smoke detectors around the world. Okay, so how they work, you've got some sort of source of alpha particles similar to the gold foil experiment we saw earlier. Okay, then we've got a couple of centimeters for the alpha particles to pass through. Then we've got another detector which will receive the alpha particles. Now, generally, you're going to have a constant flow of alpha particles, okay, and that's going to be connected to a circuit, which as long as that circuit receives a constant flow of alpha particles, there's going to be no alarm. However, the minute that we've got some smoke in the room, okay, smoke is going to rise up and then it's going to block the flow of alpha particles because the smoke particles are going to block the alpha particles, which means our circuit will be broken and that will set off the alarm, okay? Now, we can also use beta particles to ensure that the thickness of paper is maintained. Okay, so similarly, we've got here our source and here's our detector. So we get beta particles being sent from the source, and if the detector receives more beta particles, it's going to cause, that means the thickness of the paper has declined. It means it's going to cause the rollers to move further apart in order to make the paper thicker, and vice versa. Okay, so the detector is directly linked to the rollers and will send a signal accordingly. So explain why it must be beta radiation that is used and not alpha or gamma. Well, all the alpha would be absorbed and all the gamma would get through, so we would not get a good a difference in signal found at the detector if those other forms of radiation were used. Okay, so again, this is just what I've mentioned, okay, with regards to the rollers, that they will change according to the amount of radiation detected at the detector. Radiation can be used to sterilize equipment that is stored in a sealed plastic bag. Which radiation would be used and why? Gamma. It would always get through the plastic bag to reach the equipment. Okay, pretty simple. Radiation can be used to irradiate food. The advantage of this is that it lasts longer. Right, what are the dangers of a radioactive substance having a very short half-life? Well, it will have a very high activity, okay, which means it's going to emit a lot of radioactive particles per second, much more than if it had a long half-life. So what precautions do you need to take then? Okay, so remember we're talking about hospitals. There's loads and loads of people. We need to have thick shielding so probably lead-lined walls, okay, where the radioactive substances are being produced before they're given to the patients, and these need to be as far away from people as possible, okay? The dangers of radioactive substances having a long half-life are it will take a long time to become safe, okay? So this time, essentially, you know, if we've got a very radioactive particle at the start, it's going to take a very long time for it to become stable. So there's positives and negatives for both types of radioactive substances. What do you need? What precautions do you need to take for a substance with a long half-life? Well, a container that will last a long time, obviously. Clear labeling and record keeping. This is to ensure that you know when the source has been taken out and when it's been returned. So yeah, that's pretty much it. Okay.